Okay, we're moving into lesson 5.4, and in this lesson we're going to be looking at the derivatives of some trigonometric functions. So in this lesson we're focusing on sin x and cos x, and in our next one we'll look at tan x. So we're going to start off with an investigation again and figure out what the derivatives are all by ourselves. So we're going to go over to Desmos, and so you should pause the video at this point, go through the instructions, and see if you can figure it out on your own. Right, so hopefully you're all done the investigation. Hopefully you paused. I'm going to come over, and I did ask you to type in the f at x part because I'm going to use Desmos' built-in ability to find the derivative for me. So I'm typing in f at x equals sine x here, and I just zoomed to a normal zoom, and I can see the curve here repeats every 2 pi, right? My first cycle ends here at this point, but my x-axis scale isn't super helpful for me. I just want you to know that in Desmos you can change that if you go to this little wrench here on the right. On your x-axis scale, you can change what the step is. So that's like what every tick is kind of worth. So I can type in pi, and you can see it's already made an adjustment on my scale. Or if you want to be even more detailed, you can go pi by 2. Unfortunately, it doesn't go smaller than that at this point, so I can't do like pi by 3 or pi by 6 or something like that. All right, so that's a little more helpful. The next part B, says add a table by clicking the gear wheel. So again, I'm going to click over here with my function, then I'm clicking the gear wheel and adding a table. Now again, these numbers that they've put in here for the x numbers are not super helpful, so I'm going to change them to be 0, pi by 2, and notice that when I'm typing in pi, I'm just typing the letters p and I, and it automatically converts. So I'm typing P, and then once I type the I, it converts. And so now it's highlighted those key points of the sine curve for me. I can see those there. And I want to now, in the column beside f at x, just like we did in our e to the x lesson, I'm going to type in the derivative symbol here. And once I do that, I can see here that it's populated these points here. And hopefully that you recognize this curve. If you weren't confident, maybe you wanted to know what happens at negative pi by 2, you can come over to your chart in the x and type that in as well, and just keep playing with it. And now we can kind of see again that I'm getting this pattern of these x points, and hopefully you recognize it. This is the cosine curve, so if I were to type down here cos of x, it's going to fill in right on top of my derivative of sine x. So what we figured out here is the derivative of sine x is the cosine curve. So next we're going to clear all of our equations, and we're going to repeat our process for the cosine curve. So you can delete and start over again. I'm just going to come up here, and instead of sine, I'll change it to cos, and it's actually changed everything for me. So the cosine curve is now here in green. I can tell it's the cosine because it starts at a maximum and then dips down and returns to a maximum at 2 pi. And the derivative points are already on the curve here. I can see these ones here are definitely not the cosine curve. It starts on the axis. And it's not the sine curve either. So if I type in the sine curve, there it is. That's unfortunate. It's the same color. Let's change it. The black points don't line up with the sine curve either. So I'm trying to figure out, well, it's kind of like the sine curve, but it's upside down, right? It's going down and then up. So it's the sine curve with a vertical reflection, or a negative a value. And so now that I've added that -1 in front of the sine x, I can see that it's on top of my derivative points. So when f at x is equal to cos x, I notice that the derivative is the negative sine curve. All right, so we're going to summarize that into our boxes here. If the function that we're given is the sine curve, then the derivative is cos x. And if there's a chain rule involved, so if I'm taking sine of some function, maybe I've got like sine of 2x plus 3 or something like that, Then to take the derivative, I start with taking the derivative of the outer function, leaving the baby inside, right? It's like the mama is the sine, and the baby in this case is 2x plus 3. So taking the derivative of sine, I get cos, and I leave the baby inside. So the baby is called g at x. And then I multiply by the derivative of the baby. So whatever function is in there, take the derivative of it. In this case, the derivative would be 2. All right, what about if I start with f at x equals cosine x? Then the derivative, we said, is going to be the negative sine x. Now, what happens if we have a baby inside as well? So if cosine is on the outside, g at x is on the inside, we take the derivative of the outer function, leave the inner function alone inside of there, and then we multiply by the derivative of the inner function. So this is our chain rule version. All right, let's take a look at what does that look like in practice. So for my first function, I've got sine of 8x. So 8x is the baby, the outer function, the mama, is sine x. The derivative of sine is cos, leaving the inner function alone, and then I multiply by the derivative of the inside. And then I'll rearrange this. I've got a multiplication statement with 2 pieces. I want the pieces with no x's to always come at the front because they're coefficients. All right, our next one, we've got cosine of x cubed. Notice in part C, I've got cos squared of x. So we need to remember, what does it mean when the exponent comes after, and what does it mean when the exponent comes in the middle? So this means cosine of x cubed. So I would take the x number, cube it, and then take the cosine of it. This is when the squaring is on the outside. So I don't always want to have to write these brackets. So mathematicians came up with this shorthand where they're squaring the cosine of the x. So I'm taking cos of x first and then squaring that answer. So in this first case, the outer function is the cos and the inner function is the x cubed. So starting by taking the derivative of that outer function cos, that's negative sine, and I leave the inner function alone. And then I multiply by the derivative of the inner function, the x cubed. And then normally we would rewrite this with our x's in front of our sign of x's. So I've got negative 3, bringing the 2 coefficients together, x squared times sine of x cubed. So sometimes we'll put brackets around these, the argument that I'm taking sine of. It depends how complex it is. So when there's more than one piece that don't obviously go together, then I'll put brackets around it. So definitely if there was an addition or subtraction, they would be required. All right, taking a look at our next one, this time the outer function is actually the squaring. It's on the outside, and the inner function is the cos. So this is, again, chain rule, taking the derivative of the outer function, I bring the 2 down, leave the inner function in there, and subtract 1 from the exponent. So now I've taken the derivative of the outer function. Now I'll multiply by the derivative of the inner function. And then just cleaning this up, we'll bring the negative 1 to the front and multiply it by the 2. And then typically when we have a sin x and a cos x being multiplied, we put the sin x first and then the cos x. I wouldn't be as fussy about that, but definitely that multiplier with no x needs to be at the front of your string of multiplication. All right, example 2, we're going to find the critical points of f at x. This time we're combining an exponential, it's a natural number for the base, and in the exponent we've got some trigonometry. So when we're finding critical numbers, remember that that means I'm looking for where does the first derivative equal 0, or where does the first derivative not exist. So I'm considering both of those cases. So the first thing I need to do is find the first derivative. In this case, I'm going to take the derivative of the exponential is on the outside, and inside the exponent, my inner function is the trigonometry. So taking the derivative of the outer function, when I have e to the power of something, the derivative is just e to the power of that thing. And then we multiply by the derivative of the inner function, the derivative of the exponent. So I'm just going to do one piece at a time, taking the derivative of sine x, that's cos x. I can do one piece at a time here because it's just addition in between. And then taking the derivative of cos x, that's negative sine x. And so I've got my derivative here. I'm not too worried about simplifying because what I want to know here is when does this equal 0 and when does it not exist. So we're going to split it up here. Now, for when it does not exist, I'm going to look at this function here, and what I've got here is an exponential. Remember that exponential graphs look like this. So I've got that exponential piece, and then I've got a sine curve, which looks like this. It goes on forever as well. There's no domain restrictions. And then I've got a cosine curve involved, and that looks like this, and again, no domain restrictions. So all of the pieces of my function have no domain restrictions. I have no denominators, right? Domain restrictions would come from denominators. And I'm not taking the square root of anything. I don't have a log function. That would also maybe have a restriction. So I don't have any restrictions here. So f prime at x always exists. And the reason here is it's a combination of exponential and trig functions, and they have no domain restrictions. Okay, so now I'm going to go back over and figure out, well, when does this thing equal 0? So I've got a multiplication statement, so I can separate the two pieces. If something times something equals 0, either the first thing equals 0 or the second thing equals 0. All right, so we're going to solve each one of these. Now, again, when I look at the first piece here, we're going to use that trick that we used from our exponential lessons. Here I have an exponential growth graph, and I know that it has no x-intercepts. Now, this isn't a typical exponential growth graph because I have different values in my exponent, but those values are all going to be real numbers. So I know that sine x plus cos x belongs to the set of real numbers. And so e to some real number is never going to equal 0 because it's an exponential growth graph. You would have to write all that down in a sentence if you're going to explain the graph. I can't just say this is an exponential growth graph because the exponent is different. So I have to talk about how I know the exponent is a real number. Your other way to describe it is the algebraic way, which I think is a little bit cleaner in this case. So I'm just going to rewrite this as a logarithm. So I have log base e, or you could write ln here, and the log is equal to the exponent. So I know that the log is equal to sine x plus cos x, and I'm taking the log base e of the answer to the power, so it's of 0. And I know that log base e has no solutions, it's undefined. Oh, sorry, log base e of 0 is undefined. So therefore, there are no solutions to this part. All right, so we have to solve this part here, cos x minus sine x equals 0. So there's a few ways that we can do this. What I'm going to do here is, because I don't have anything that I can factor on this side here, I have a linear, and I'm in a bit of trouble here because they both involve an x term. But what I'm going to do, since they're trig, is I'm going to move it over and say that cos x is equal to sine x. And then I'm going to use my knowledge of trigonometry. So I know that I can divide out the cosine x here. So I can divide out cos x. I can't always divide by cos x because then I might be dividing by 0 sometimes. Remember that my cosine graph up here, sometimes it does have a height of 0, and I can't always divide by 0. So my justification for why I can is because cos x does not equal 0 when the original statement is true. So for all those x-intercepts of cosine x, they're not also going to be x-intercepts of the sine curve. These guys have different x-intercepts. So I know that it will never equal 0 when the original statement is true, so I can divide by cosx. And so then this gives me on the left 1 is equal to tan x on the right. And now I can solve this. This is a special triangle for me for when tan x is equal to 1. So I'm thinking back to my special triangles, and this is my 45-degree angle triangle from grade 11, or your pi by 4 triangle from advanced functions. I know that this is 1, 1, and root 2. So for my tan ratio, that's the opposite over the adjacent, so it's 1 over 1. And so I know that my angle here is pi by 4. That's my related acute angle. Now I need to figure out what quadrant am I in if tan of x is equal to positive 1. So because it's positive 1, I know that I'm either in the A quadrant or the T quadrant, and my beta, my pi by 4, is between the terminal arm and the x-axis. And so I get two different answers. My x1 is going to be equal to pi by 4 plus, or sorry, pi by 4. But I could also rotate around and then out up to that terminal arm. So I could add an extra period, or I could add 2 periods and circle around twice and then go. So I'm going to continue to add extra periods here. And the number n has to be an integer number. So n belongs to the set of integers. I'm going to put that at the end here. For x2, I'm coming around to this terminal arm. This one here is going to be pi on top plus a pi by 4. So that's 4 pi by 4s on top, plus an extra one down here. That's 5 pi by 4s. And again, I could rotate around a certain number of periods, or I could go backwards a period and then around to my terminal arm. So I could also subtract. So n could be any positive or negative whole number. So n belongs to the set of integers. And so then, therefore, what we figured out is we had no answers from f prime does not exist. We had no answers from this section here. So these are my answers. This question does ask for the critical points. I'm going to leave it at critical numbers because the heights are going to be changing because there's an exponential involved. So it's not like they're always across the same level curve. So I'm going to change the question up here. I wouldn't ask you something like that. Oh, it is numbers. Sorry. I did change it. All right, moving on to example 3, we're finding the equation of a tangent. So back to, like, we've seen this question a bunch in a lot of different chapters. I need point and a slope. And we've got our equation here, g at x. So g at x involves a product of something with x's times something with x's. I know that to find the slope, I am going to need to find the derivative. I can also find the point right away. So my point, I'm just going to plug the x value into the original equation. And so I get 3 pi by 4 times sine of 3 pi by 2. So remember that on the sine curve, 3 pi by 2 is this point here. And so there's a height of -1. So this second piece here is equal to -1. And so my point is 3 pi by 4 comma -3 pi by 4. So we'll use that later on. Okay, so we need to find the slope of this function. I'm going to take the derivative. I know that the slope of the tangent is equal to the derivative. I'm going to use a product rule here. So I'm thinking about u and v, and I'm going to do u prime v plus uv prime. And the derivative of the first thing is just 1 times the second thing. And then we'll add. This time I'm going to leave the first thing alone and take the derivative of the second thing. So I have a chain rule here. The outer function is sine and the inner function is 2x. Taking the derivative of the sine, I get cos, leaving the original inside, and then multiply by the derivative of the inner function. Okay, so all together here I've got sine 2x, and then cleaning this up, I'll bring the 2 to the front. Okay. So you'll find that often when there's a multiplication of two, like just a coefficient and an x variable, we don't put the brackets around it. But if you want it to be really clear, you can keep these brackets in. All right, we need to find the value of the slope at the given x value. Okay, so we can simplify these guys. Remember, when I have 2 over 4, that's just the same as over 2. And so we've got sine of 3 pi by 2 plus, again, same thing here, I've got 3 pi by 2 times cos of 3 pi by 2. All right, we already know that sine of 3 pi by 2, we already talked about it over here, it's -1. And so we need to figure out, well, what's cos of 3 pi by 2? So I'm just thinking about my cosine graph. And this point here is the 3 pi by 2. So I know that I have a 0 value there. So I actually get a slope of -1, which is kind of nice. So now we're going to put this all together in our equation. The equation is going to be y equals, so we'll take our slope number times x plus b, and then we're going to sub in the point. All right, when we rearrange and solve for this, I'm going to get 0 is equal to b. So therefore, the equation is just y equals -x because the b went away. All right, have fun with the homework today.